Now that you know how to draw the Lewis structures, we're going to take a look at something that we call their molecular geometry. And so the molecular geometry is the three-dimensional arrangement of atoms in a molecule. It's basically the correct shape. And this is important because the shape of a molecule influences chemical and physical properties of that chemical compound, like the melting and boiling points, if it's soluble, its density, as well as the reactions that it can undergo. And so this molecular geometry is based off of something called this valence shell electron pair repulsion model, which we just call VSEPR because that's a lot of words to say all the time. So as a reminder, your valence shell is the outermost occupied shell of electrons in an atom. So your VSEPR theory says a molecule will adjust its shape so that the valence electron pairs stay as far apart as possible from each other. And this is because like charges repel one another. So a minus is going to repel a minus, whereas a minus and a plus would attract one another. So we look at the number of bonding pairs of electrons and the lone pairs around the central atom because that's what's going to influence the shape. And so when we look at the VSEPR theory, double and triple bonds in terms of electron repulsion are no different than a single bond. So that means if you have a double bond, it's not going to repel electrons any more strongly than a single bond would. They repel electrons equally. So what we're going to do is we're going to take a look at a few possible geometries. And so when we do that, we're using this general form, and we're using A's and B's. So A will indicate your central atom. So here would be your central atom, and B indicates the atoms surrounding that central atom, so B2. So in this particular example, we have AB2. So this says we have a central atom with two other atoms surrounding it. And so your example, your real life example is beryllium hydride. And so its Lewis structure looks like this. And we could have carbon dioxide whose Lewis structure will look like that. And then our overall shape, notice that we have no lone pairs of electrons. And so we have just a straight linear model. And so we call this, the geometry is referred to as linear because it makes a straight line. And the bond angle, so on a straight line from your geometry math class with Miss Klingfist, that angle is 180 degrees. And so when we refer to our bond angle, we are talking about the angle of the bond right here. So here's your bond angle. So when we look at a chemical formula, the subscripts after the B element, whatever that may be, will tell how many atoms of B are bonded to the central atom. So we've kind of been working with this already. We know that when we have two elements, one single and then multiple of the second one, they all bond to that central atom. So don't forget that as we go through this. So another possible geometry would be AB3. And now we have three atoms bonded to that central atom. And now we have our molecular geometry looking like this. Kind of like a triangle almost. And so our bond angle, so from here to here or here to here in this diagram, they're both 120 degrees. And we call this shape trigonal planar. All four atoms lay on the same plane. So if you were to lay this on a piece of paper, all four of these atoms would touch that paper. There's no real 3-dimension to it. It's pretty much a 2-dimensional structure. Methane, or AB4, because now we have 4 atoms bonded to that central atom, they no longer lay in that same plane because we want to maximize the distance between the hydrogen atoms. And so we now have this one atom that sticks up. And we call this shape, or its geometry, this is really the geometry still, tetra for 4, tetrahedron, or sometimes it's also called tetrahedral. They're the same. And our bond angle between these is now 109.5 degrees. Sometimes you'll see these drawings now like this, and so what you should notice is that this bond and this bond are drawn with the same regular lines. That means those 2 atoms are on the same plane. And then we have this dashed and this kind of solid triangle. That means those 2 are laying on different planes. So on this particular structures, we have atoms on 3 different planes because we can tell by the different bond diagrams or bond symbols. Our next geometry is when we have the general form AB5, or 5 atoms bonded to that central atom, and we call this trigonal bipyramidal. So the bond angle for these 3 atoms right here is going to be 120 degrees. And we call those 3 atoms the equatorial atoms because they all lay on the same plane. And so remember, when we talk about being on the same plane, if you were to put this structure on a piece of paper, all 3 of these would touch that piece of paper. The other 3 atoms that we have, these 3, they are your axial atoms. They lay perpendicular to the equatorial atoms. Okay, so in this diagram here, these 3 are your equatorial, and then these would be now your axial because they're that 90-degree angle. And so we have a very 3-dimensional structure. And a little bit about the name, you can see that we have kind of 2 triangles going on, the top one and this bottom one. And so that's where we get trigonal because of the triangles. And then bi for 2, and pyramids because we have 2 pyramids stacked on top of one another. All right, next shape, AB6. We now have 6 atoms around that central atom. And so we get a structure that is octahedral in shape. And all of the bond angles are now 90 degrees. They're all separated by 90 degrees, perfectly that squared. All right, now notice all of those examples had 0 lone pairs. And so now we're going to look at some diagrams that have lone pairs of electrons. And so in order to do this, we look at the electron domain geometry. And this is the total number of electron pairs bonding and the lone pairs. And so now we use this E to indicate lone pairs of electrons. So AB2E is for ozone, and you can see the two structures here. Notice that they're resonance structures. And on that central atom, we have one lone pair of electrons. When you have lone pairs of electrons, they're going to be slightly more repulsive than the bonding pairs of electrons. They take more space. And so what they're going to do is they're going to force the side atoms further away, because these electrons really don't want the other electrons near it. So it's kind of forcing them away. So you'll notice that we have a much larger angle up here because of those lone pairs of electrons up there. So we have a little handy dandy chart for you, and I actually think in your notes I have this on there twice. And so what you can do is, once you've got your Lewis structure drawn, you can look at the chart and see, all right, how many pairs of electrons, or total number pairs of electrons do you have? How many of those are bonding? How many of those are lone? And then this chart tells you the electron domain geometry and the molecular geometry of each of those. This chart tells you if there is no lone pairs, their electron domain geometry and their molecular geometry. So these two are nice little cheat sheets, but they're only helpful if you've drawn your Lewis structures correctly.